Hey, ladies and gents, welcome back again. We are going to obviously continue to talk about parabolas, quadratic equations. For this lesson, you'll need your workbook or access to it online. If you want to get on Agile Minds website, once you are there, my courses, you're going to look for, show it here, Unit 8 on the left side under Course Contents. Hit the drop down arrow next to 22, Topic 22, the drop down arrow next to Lessons. And we are at Lesson 7. We are at Lesson 7. Your front page of Lesson 7 will look a little bit different. I'm already on page 3 within that lesson. So to get to page 3, you're going to hover over those 3 dots, and then you can click right there on page 3. You'll also want a graphing calculator. Hopefully by now you followed the instructions I've had on Canvas for accessing a graphing calculator at home. Yours should look like the one, your graphing calculator at home should look like the one that I used to project from at school. It is going to have more screens than just this, but you'll have this same format right here. So this graphing calculator, absolutely helpful. I am going to use that in instruction. If you have not yet accessed this on your school computer at home, then do me a favor, stop this video right now, and under Canvas modules, click on the module that talks about calculator access and follow those directions. If you have any issues, please let me know. Yes, you can use the Desmos graphing calculator in here. However, I am also going to show you some, whoops, wrong screen. Hey, double Mrs. P, look at that. I'm going to show you some TI-84, the calculators we use in class, some specific information on how these calculators work that does not apply to the graphing calculator built into Desmos. So hopefully you have everything you need. Today we are going to answer the question, why quadratics? Why parabolas? What are they good for? What do they model? What do they show us? Well, as I alluded to before, you see quadratics all the time. I'm going to guess that every single one of you has been to McDonald's, and those McDonald's arches are 2 parabolas side by side. Now, I'm pretty positive that with the number of McDonald's out there, it is not the same person that goes and designs every single one of those arches out in front of the restaurant on a stick. There's just way too many of them. But did you know that there's actually an equation programmed into a computer that creates those arches so they look exactly the same from store to store to store? That equation that produces those arches would have to be a parabola because of that U-shape. It'd have to be a quadratic equation. It would have to have an highest exponent of 2. If any of you have been to St. Louis, the St. Louis Arch is an example of a real-life quadratic equation. Now, if you wanted to know how high the St. Louis Arch is, yes, I realize you could Google it, but when it was created, nobody could get to the top of that St. Louis Arch and just drop down a measuring tape. There's no measuring tape that large, but there's an equation that they use to help build that St. Louis Arch that you can use to figure out how tall is the arch. That equation also allowed them to figure out where supports needed to be and other things like that. So architects would use quadratic equations in the building process. Now, quadratic equations, and we're going to see now as I'm going to flip around my screen, we are on page 286 in your workbook. And again, if you don't have your workbook at home, if you didn't grab it on Friday or you weren't there when we did leave school, hey, Mrs. P, then in the very first video, April 7th, maybe, I don't have my calendar next to me, the very first video there right above the picture you see on the screen, there's a video of me showing you how to access this workbook online. So here we go. Why else quadratics? Quadratics actually model the pathway of anything that you throw, anything that really flies, anything that you hit. Think about passing a football, throwing a water balloon, hitting a baseball. Anything like that has that arching pathway as it moves is modeled by a quadratic equation. So let's focus on this one. A science class launches fireworks. That sounds fun, other than it's highly illegal in Illinois. But hey, it's cool. Sandra's science class launches firework rocket from the ground. In the table, they record the height of the rocket in feet. So there's the height of the rocket and the time, specific times after the launch. So let's see what we can answer about this. So think about launching a firework rocket. I'm going to draw a picture. If I launch it, it's going to start on the ground. I'm going to launch it and it's going to go up. But I'm not going to just draw the picture like this, because if I just draw a picture like that, then that's telling me that the rocket's going to go up and it's going to come back down without ever covering more distance. Instead, the rocket's going to most likely do something like this and come back down. Now, two things can be said here. I could say that I'm covering height and I'm covering horizontal distance. This also, maybe you do have a rocket that goes up and down in the exact same place. This could also show me a vertical distance of my rocket over a time period. But regardless, this is definitely a parabola. It is definitely that U shape. So at time 0, the height of the rocket is 0 feet. What does that mean? Well, if you're not starting the clock and you have no height, has that rocket gone anywhere? No, because time hasn't started and it's on the ground. This would be my starting point. 0 feet covered, 0 time. It's my starting point. My purple pen is running out here, and Amazon should be bringing more of them here shortly, but I might have to move to a black pen later in these notes. Based on the data of this table, what type of function can be used to model the data? We've already talked about it. It's quadratic. Now, it does say how does the table show that? Now, these are some rather large numbers, so I'm not going to go all the way through here. But we know that in a table, a quadratic function should have a common second difference. So to get from 0 to 144, I add 144. To get from 144 to 256, we add 112. Now, it's definitely not linear because they're not the same. And again, we already know that this is quadratic, so we don't have too much guessing here to do. But I just, again, want to show you what does a quadratic table pattern look like. 80. And then to get from 336 to 384, we're going to add 48. Now, really, I should go all the way through the table, but just because these are large numbers and it's a large table, I'm going to stop here. Quadratic patterns should have a common second difference. These didn't match the first time, but the second time, to get from 144 to 112, we're going to subtract 32. To get from 112 to 80, you guessed it, we're subtracting 32. And to get from 80 to 48, again, we are subtracting 32. We know that quadratics are represented in a table by having a common second difference. Based on the table, what is the maximum height of the rocket? Okay, now you may be thinking, how am I supposed to know which one is the maximum? Well, think about what the word maximum means. It's the highest. So if I look at height, my highest height is actually going to be, bingo, right there, 400 feet. Maximum means highest, so it has to be 400 feet. Anything else surrounding that is lower. Based on the pattern in the table, what is the height of the rocket at 9 seconds? Man, our table does not go all the way to 9, but many of you have probably noticed there is a pattern here. If you take a look by that 400, on either side, we have a 384. Go one step further. After the 384, we have a 336 on each side. So if I was to continue this up to 9 seconds, let's see, I'm missing 8. 8 would have to match 2. That would be 256, which means 9 would have to match 1, which is going to be 144 feet. We've talked about the symmetry of a parabola before, and that symmetry always comes out in a table. So the cool part is with these tables, you can continue to expand them even if you don't see all the data just based off the symmetry. Once you identify that maximum or minimum, depending on the shape of the parabola, it's going to be symmetric, mirror imaging, mirror points all the way through the rest of the table. So with that said, we are going to move on to another application. We are going to move down here to core activity. However, for me to do this, I also want to use your Agile Mind website. So I'm going to flip this guy around. And here is where on Agile Mind, I'm going to be on page 3, and we're actually going to move to panel 2 down here. I will show you my book here shortly, but you may want to fill out as you watch this video. So Vincent and Bobby have made a water balloon launcher, and their younger sisters are often picnicking underneath their treehouse, so they want to surprise them with water balloons. Probably sounds familiar with some of you. So we have a table to show in our book. We have a table to show the relationship between time and balloon height. As time passes, their balloon should go higher. You can see it launching in there, and the table is filling out. 0 seconds, 0 feet, 0.5 seconds, 28. And I'm going to keep just copying the table, and hopefully you are doing the same in your workbook. 60, 48, and it looks like this this question mark here is 3.5, which we have in our table in the workbook, and it says 0 here. Now, whoops, how did I know that this? Oh, wait a second. Actually, I'm going to flip this back over. So I want to make sure that you guys have yours filled in through a time of 3. I'm going to flip mine back over. Here we go. I kind of crossed this one out. Is 3.5 really going to have a height of 0? Really great question. Now, if you think about that pattern within the table that we talked about in the previous example, we can figure out our answer. So first thing I want you to do is locate the highest point of this water balloon. How high does this water balloon go? Looking, our highest value here is 64. So I'm actually going to plot this as a picture as well. At 2 seconds, so this is going to be my x value, I am at, so there's my x, there's my y. X's always come first in a table. So 2 over, I am 64 feet high. So there's 60, there's 65. 64 is going to be right underneath 65, best you can. At 1.5 seconds and 2.5 seconds, I'm at 60 feet. So 1.5 is the second line in. 1.5, I am at 60. 1.5, I'm at 60. But at 2.5, I'm also at 60, plotting those points. Okay, so we did these. At 1 minute, I'm at 48. So 1 over, there's 45. 48, you're going to have to estimate. We just did that one. At 3, I'm at 48. So 3:48. So our next one is at a half a second. I'm at 28. So a half over is actually 2 tick marks in. 28 up, which tells me 3.5. Yep, you got it. Also has to be 28 because of that symmetry. We've talked about the line of symmetry that goes through the maximum or minimum of a vertex. Whatever happens on one side has to happen at the other. So at 3.5, I also have to be 28 up, which means at 0, 0, my starting point, I must be at 0 by the time I hit 4. Hey, look at that parabola shape. I'm going to go ahead and play connect the dots. Okay. I want you to go ahead and copy down. This is an equation. I don't expect you to be able to write that equation at this point in time, but I expect you can copy it down. That way you have it. If you wanted to graph this equation in your graphing calculator, you're going to find that you get exactly the same picture. We will move to the graphing calculator on our next example. So what is an appropriate domain? We know domain refers to the x values. You may say, because we've talked about it before, parabolas have a domain of all numbers. You can plug anything in and square it, but think about real life examples and think about what our x values and our y values represent. X represents time. My question for you, can you have a time of -1 seconds? The answer is no. Whoops, I just threw my pen at my computer. Time has to be positive. So for my domain, I'm going to say positive x values. Positive x values. Okay. Range, we know, refers to my y values. Y is doing it again with my pen, look at that, is the height of my water balloon. A height of 80 makes sense. Not that we've got that high. A height of 60 makes sense. A height of 0 even makes sense, meaning we haven't thrown anything at all. But does a height of -10 make sense? Does a height of -20? Answer is no. Real life situations, you always have to consider what is realistic. In this case, it's not realistic to have any negative y values. It's not realistic to have any negative x values. We are going positive all the way around. So we have to ask the question, what equation, well, we already have an equation right here, models the situation when the height is 0 feet? What equation models this situation when the height is 0 feet? So let's think about height. Height, according to our table, is a y value. So if I wanted to plug this into an equation, where would we plug in a 0 for y? We'd plug it right there for y. Plugging in a 0 for y, this is the equation that would tell me when I have a height of 0 feet. Now, solving this, how are we going to solve it? That's actually something we are going to answer later on, because we've never really solved equations that have exponents. Every equation we've solved this year up until now hasn't had an exponent. So we'll talk about solving this later on. When will the balloon hit the ground? Well, think about your height if you have hit the ground. You've thrown a ball, it's sitting on the ground. What's its height? Its height is 0 feet. So if I look at my picture, we know right here I'm at 0 feet, but is this when I've hit the ground? No, this is before I even threw the water balloon. The water balloon. I throw it, it goes up, 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 reaches its maximum point, our vertex. It's going to come down, 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 down. And when I hit this value of 0, now I know I have hit the ground again. And this time we are at a time of 4 seconds. So something else to consider. We have this equation that models the height of 0 feet. Look at our graph. How many times do we have a height of 0 feet? 2. So how do we solve an equation and get 2 answers? Well, we're going to focus on solving an equation on a graph for a couple more examples. We'll focus on solving the equation based off the actual equation later on, kind of like what we have done up until this point. Everything we've done for solving purposes has been graph, calculator first, and then we go to the algebra later. So to get 2 solutions, solve for a height of 0 2 times, 4 seconds is when it hits the ground, and 0 seconds before it even starts. Okay, moving on to another example. This time, Bobby and Joseph are dropping a water balloon from a height of 10 meters. I'm going to flip this over, go back here, and I am going to go to page 8 on Agile Mind site. So you see a little visual of, what are their names? Again, Joseph and Bobby dropping their water balloon. So up there, maybe in their apartment building, they decide to drop it. Hopefully they weren't aiming for anyone in particular. They drop it, boom, splat on the ground. Kind of fun. You can keep hitting it. So what do you think that graph, if you were to create a graph that would mimic the balloon's pathway, what would you expect it to look like? I'm going to flip this back over one more time. If you want to keep hitting that arrow and keep dropping the water balloon, go for it. Have fun. Well, I actually am giving you already the equation for Bobby and Joseph's water balloon and dropping it. And what I'm going to do, so I want you to write this down, 10 minus 4.9 t squared. So what do you think that t stands for? Well, t is going to be time. How long was that water balloon in the air? And h is going to be height. If you also want to write y and x by these, you can, if that makes your life a little easier. We know this one would be our y and this one would be our x. Let's put this in our graphing calculator. So I'm going to use the school one. Again, if you haven't gone through accessing this on your home or your school device at home, please go back into Canvas and follow those steps for getting this on your device at home. So instead of t, I'm going to type in x and squared, and I'm going to go ahead and hit graph. Okay, and I want you to go ahead then and sketch a graph of what you see on the little calculator screen in your workbook. Okay. So our next question was, I just sketched what I saw on my calculator screen. There's that parabola shape that we expected. Use the graph to estimate how long it will take the balloon to hit the ground. Okay. The balloon hitting the ground, we know hitting the ground, I should have a height of 0. If I'm on the ground, I have no height. So a height of 0 would mean I have a y value of 0. A y value of 0 would be this point here and this point here. Now, before we actually, I'm going to go back to the calculator in a second. Let's consider this one. This one would also have a x value, which x is going to be my time, or t. This would have a negative x value. Can we have a negative time? The answer is no. Joseph and Bobby had dropped the balloon from the top of the building. Their balloon did not actually travel in a negative time manner, nor did it go underground. This side should never really have existed for Joseph and Bobby. They dropped it from the top of the building and down it went. So when I wanted to figure out how long it will take the balloon to hit the ground, I want this value right here. So back to my calculator. Now, my calculator, I could just hit this side arrow and I can kind of hover over right there. It looks like 1.4. Now, ready? If I want an exact value, there are some steps you can take, and I will write them out in the book. If I want to know an exact value where I'm crossing this x-axis, then in my calculator, I'm going to hit second. I don't think I hit it well enough. Second, calc. There we go. Second, calc, which is the trace button. So I'm actually going to write that out in the workbook. Second, trace, and I want option number 2, 0. Now, notice the instructions on the bottom of the screen. It says left bound. What that means is we want to make sure that that little spider blinking cursor is to the left of the intercept of the point that we want. So the point that we want, yes, this is above it, but it's also to the left. I'm going to hit enter. Notice that line that shows up. As long as that line is to the left of the point you want, you know you did it correct. If it's not to the left of the point you want, then you're going to have to hit second calc number 2 and try again. Now it says right bound. So I am going to hit my right cursor until I am to the right of the point I want. It doesn't matter how far, doesn't matter how close. I usually go a little further to be safe, and I hit enter. Now, why do you think we have to have the calculator go right and left? Well, as we talked about before, there's 2 places on a parabola where we can have this y value of 0. So by doing left bound and right bound, we're telling our calculator which one we want. Now it says guess. So I'm just going to move my cursor a little closer. Doesn't have to be perfect. I'm going to hit enter and take a look at that. It tells me that we will hit the ground at a t value or an x value of about 1.4. So about 1.4 seconds. I'm going to switch back to here. I wrote down the steps for the calculator. You probably want to write that down. I approximated right here. So what did we just found? You saw that I used the word 0 in the calculator to help me find where I was crossing my x-axis. So a 0 in math is a point or points where a graph crosses the x-axis. Now, you've probably also heard before that the word crosses, there's another way to say crossing, and that's intercept. An x-intercept is exactly the same as a 0. It's exactly the same as a 0. Why in math should we have more one name for something when we can have 3 names for something? A 0 is the point or points, I don't know why I put 2 S's in there, where a graph crosses the x-axis. An x-intercept means the same thing. The word intercept means crossing, so an x crossing. We cross the x-axis. That's my x-intercept, same as a 0. Now, solution. I'm going to go back one. If we had to write an equation that can be solved to find when the water balloon hits the ground, well, we know again, hitting the ground means we have a height of 0. So the equation we would be solving is 0 equals, and I'm going to look up at that equation I had before, 10 minus 4.9 t squared. This equation, take a look at the right side. That's what I put in my calculator, y equals. This says find me a y value equal to 0. Well, isn't that what we found here? A y value, a height, equal to 0. A solution is also the same as a 0. If you hear anyone tell you, find the x-intercept for your parabola, where do I cross the x-axis? If you hear anyone say, find the 0 for your quadratic equation, where do I hit the x-axis? If anyone says, solve the equation. Now, yes, we're going to learn how to solve this algebraically without a calculator, but if you see your highest exponent is 2 and someone says, solve, find me the solution, you're looking for your 0. You're looking for your x-intercept. Where am I crossing that x-axis? So with that said, we're actually going to move down here to the consolidation and we're going to finish up. Now these ones, they're quadratics. I know it's quadratic because of that highest exponent of 2. I know it's quadratic because of that highest exponent of 2, but there's no story about a rocket, fireworks, a water balloon, anything like that. This one says, use the graph to solve the quadratic equation, negative x squared plus 4 equals 0. Well, a couple things I want to point out. Hey, that negative, that's what flipped my graph and is making it open down, just talking about those transformations. The plus 4 is what moved my vertex up 4. But we want the solutions. Well, think about what solutions are. Solutions are when we replaced that y with a 0. I want to know, where do we have a y value of 0? Well, a y value of 0 means we have not gone anywhere up or down, which means we are still sitting right here on the x-axis. And notice with our parabola, there are 2 places where we're sitting on the y-axis. We are sitting on the y-axis at the point negative 2 over y value of 0 and 2 over y value of 0. I have 2 points where I have a y value of 0. Another way I could write this answer, remember when we solve equations, we're solving for x. I could also write this as x is equal to 2 and x is equal to negative 2. I can write these solutions as x equals. I can write them as points because on the graph, these solutions are indeed points. Now, looking at the table, how would I use this table to solve the quadratic equation x squared minus 9 equals 0? Well, this means I have a y value of 0. So in my calculator, I'm going to look for a y value of 0. And I see that here, and I see that here. Because again, we know with parabolas that should happen twice. So we have the points negative 3, 0, and 3, 0. Or I could write it in solving form, what we're used to. An x value of negative 3 would give me a y value of 0, and an x value of positive 3 would get me a y value of 0. Solutions, x-intercepts, zeros, all exactly the same thing. So here's what I would like you to do. If you have more questions, you know what? I just flipped the page. I think there's one more that I want to do with you guys. Before I tell you what I want you to do, I want to do one more. This one's a good one. Jocelyn's sister, this is page 288. Jocelyn's sister tells her that the table of values right here is a quadratic function. Jocelyn knows that the graph of a function is going to be a parabola, so that U shape, and there is a line of symmetry at an x value. Help her find an x value at the line of symmetry. Okay, what the heck does that mean? So U shape. If I look at this, I have values that are pretty high, but I only have one low value. This kind of tells me that I most likely have a parabola that opens upward. Had I even drawn it opening downward, not a huge deal. If I wanted to actually plot points because I have them, I could create a graph and do that as well. We know that the line of symmetry is wherever I can draw a line and the left and right sides of my parabola look exactly the same. We also know that that line or axis of symmetry always goes through the vertex. So how can we find the vertex on here? Well, our vertex happens to be the smallest or the lowest point. 10, 10, 7, 7. If I watch this pattern of y values, they're getting smaller, smaller, smaller. When we hit 6, they start getting bigger, bigger, bigger. So if I look at the graph, my y value is getting smaller, smaller, smaller. They hit 6 and they go bigger, bigger, bigger. Now, does that mean that my line of symmetry is at 6? No, because 6 is not an x value. 6 is a y value. Okay, so then what x value? Well, the x value that partners with this vertex is -2. So my axis of symmetry happens to be at -2. If you remember when we were talking about parts of a parabola, my vertex is the point in the middle, but my axis of symmetry is the line that cuts it in half, and that axis of symmetry goes through the x-axis. I also remember that because there's an x in axis. Axis of symmetry goes through the x-axis. So when we're talking about my line of symmetry, it's always my x value. Okay, thanks for bearing with me. I will tell you that I'm going to go ahead and complete 3. I would encourage you to stop the video when it's all said and done and try number 3 on your own as well. 3 is not homework at all, but if you just want some more practice, I will include 3 in the PDF of my notes, which is linked here in Canvas. Your homework, and again, you'll see this on Canvas, is going to be completing number 1. You have 2 parts in number 1. You have both A and B. You will notice that number 1, A and B, are very, very, very similar to the 2 problems we did at the bottom of page 287. So look at page 287. You are also going to complete number 2 for me, talking about the parts of a parabola, finishing it being symmetric. So don't just randomly draw it. Use points to make sure it's a mirror imaging. And then the other one you are going to complete for me is on page 290, number 4, but go ahead and cross off D. We're not going to do D. Number 4, just A, B, and C. Give those a whirl. You're going to submit them on Canvas. Use the link here in this Canvas description, and I will give you some feedback as soon as I get it. See you later, kids.